In this lesson, we are going to revisit our square roots and cube roots. Let's start with our squares and square roots. And so if I have some visuals here, I have a square of side length 1, a square of side length 2, 3, etc. And so if you know the side length, if you multiply it by itself, you get the area of the square, right? A side length of 2 gives you 4 square units, side length of 3 gives you 9 square units, etc. We call all of these areas, whoops, I didn't multiply that right, all of these areas perfect squares or square numbers, right? So if this number is the product of two whole numbers, then we have a square number or a perfect square. If we take the square root of that number, or in other words, the square root means if we break that number into two identical factors and we take just one of the factors, then we call that the square root, right? So the square root of 4 is the side length of the square. The square root of area 9 is the side length of the square. Okay, so a reminder, a perfect square or square number is a number that can be expressed as a product of two equal factors. A square root is one of those two equal factors, right? So the factors don't actually have to be numerical, they could be variables. If n squared is a square number because it can be written as the factor of two equal factors, right? And one of those factors being n. Same thing with cubes. If I have varying size cubes of side length 1, 2, 3, 4 all the way to the nth side, then the volume would be length times width times height, or 1 times 1 times 1, which is 1, etc. 8, 27, 64, n cubed. All of these volumes we call perfect cubes, or cube numbers. When you take the cubed root of a number, you get the edge length of the cube, right? For example, the cubed root of 27 means to break 27 into 3 identical factors. That's what the cubed root means. And so to take the cubed root of a number, you take one of those 3 identical factors. Okay? So we know that a perfect cube or a cube number is a number that is a product of 3 identical factors, and the cubed root of that cube number is one of the 3 identical factors. So if I ask you if a number is a perfect square, you could tell me by saying, well, can it be broken into 2 identical factors? And by using the square root function, when I type that in, I get 15. It means that the square root of 225 is equal to the square root of 15 times 15, take one of those. Right? So that's why in your calculator you get 15. Okay? And if I give you another one like this, you just type it into your calculator, 22050, and I would get this. And since I'm getting a decimal, it means that this is not a perfect square. I cannot write 2 whole number factors, right, to create that. So this is not a perfect square, but this one is. What about something like 3 to the power 4? Well, I could calculate 3 to the power 4, get 81, and then square root it. Or I can say, well, can I just break that into 2 identical factors? Well, sure, I can break it into 3 squared times 3 squared, right? So since I can break it into 2 identical factors, then it is a perfect square. The square root is one of those, which is 3 squared or 9. I could do it with a variable rather than a number. Can x squared be broken into 2 identical factors? Yes, it can. We know our exponent laws. We know that x to the power of 3 times x to the power of 3 is x to the power of 6. 3x's multiplied by 3x's is equal to 6x's. So therefore, the square root of x to the power of 6 would be just one of those, or x to the power of 3. What about 9 to the power of 6? Okay, well, we could go to our calculator, type in 9 to the power of 6, and then take the square root of it, Or we can use our idea that we just used. Well, I can break it into 9 to the power of 3 by 9 to the power of 3. Instead of x, I'm just using 9. So therefore, the square root would be 9 to the power of 3, one of those two equal factors. Okay. Can x to the 5, x to the power of 5 be broken into two identical factors? No, I can only break it into 3 and 2 or 4 and 1. So since I can't break it into two identical factors, it is not a perfect square. Okay, so we're seeing that when we're looking for a perfect square with exponents, what do we notice has to be true with our exponents to be able to break it into two equal factors? Our exponent has to be even, right? Because 2 and 2 make 4, 3 and 3 make 6. I can't make 5 with two equal numbers because the exponent laws say we have to add the exponents to when multiplying. Okay? So, if I gave you a product of a bunch of numbers, so if this is called the prime factorization of a number, what any number, for example, 15, can be broken into its prime factors 3 times 5. Therefore, 15's prime factorization is 3 times 5. I can break any number into a product of primes. If I was looking at 45 instead, it would be 15 times 3, which is 3, and that 15 keeps breaking down. Oh, there's 2 3s and a 5, right? And so that's the prime factorization for 45. This is the prime factorization for whatever number all those multiply to give. Can we use the prime factorization to see if it is a perfect square or not? Well, we just like we did above, we just look at each factor separately. Can I break 2 to the power of 6 into two groups? Yes. Can I break 5 into two groups? No. Since I can't break 5 into two groups, it is not a perfect square. Okay? What about this one? Well, I can break 3 to the power of 4 into two groups because it's even exponents, 3 squared and 3 squared. I can break that one, and because all of the exponents are even, right? So I could break it into 3 to the power of 2, 1 5, and 6 11s. Multiplied by itself twice. And since I can break it into two equal groups, it is a perfect square. If I asked for the square root of it, you would just take one of those groups to be the square root of that number. Okay. I could combine numbers and variables, right? Is 16 a perfect square? Can it be broken into two identical factors? Yes, 4 times 4. What about y to the 10? Can that be broken into two? Yes. Y to the 5 times y to the 5. Oops, that's not 5. There we go. So yes, that is a perfect square because it can be written as 4y to the power of 5 multiplied by 4y to the power of 5. So if you can make two equal groups of factors, it is a perfect square, which you can then take the square root by taking one of those factors. Okay, that's just a recap. What about a perfect cube? Well, a perfect cube, you need to look for the cube root function on your calculator. Can you find that cube root function? Okay, and type that in. So if I typed in the cubed root of 3,375, I am getting 15. Right? The cubed root of that is 15. So it is a perfect cube because when I type it in, I get a number without a decimal, right? What about 640? If I typed in the cubed root of 640, I get 8.6 dot dot dot, a whole bunch of decimals. So this is not a perfect cube because it is not three identical factors multiplied. This decimal we'll learn in the next lesson goes on forever, like pi with no patterns, so it is not a perfect cube. 4 to the power of 3, well, can I break 4 to the power of 3 into three identical factors, right? This time it doesn't need to be broken into 2, it needs to be broken into 3. Well, 4 to the power of 3 is 4 times 4 times 4, so yes, it is a perfect cube because there are three identical factors. What about x to the 6? Can that be broken into three identical factors? Well, I could break it into three groups of 2, right? If I multiplied that, I get 6. 2 plus 2 plus 2 is 6. So if I asked for the cubed root of that, I would just need one of those three identical factors. Could I break 10 into three equal groups? x to the 3 times x to the 3. Nope, I get 9 there, and if I put one more 3, I get 12. So that is not a perfect cube. How can I tell by just looking at the exponent if it's going to be a perfect cube? Well, if you're going to make 3 equal groups, and Powers laws say when you're multiplying, you add those, that means that needs to be divisible by 3, right? You make 3 equal groups. So if your exponent is divisible or a multiple of 3, then it is a perfect cube in the exponent. All right, let's keep looking down. So 6 to the power of 9 is, because 9 is divisible by 3, so I can make 3 6s in each group. So therefore, the cubed root of that is 6 to the power of 3. And again, I can mix numbers, and I can mix variables. I would just look at the numerical part of your term first. 216 can be broken into 6 times 6 times 6, so 216 is a perfect cube. And x to the power of 12 can be broken into x to the power of 4 times x to the power of 4 times x to the power of 4. Therefore, 6x to the power of 4 3 times is equivalent to 216 to the power x to the power of 12, so therefore it is a perfect cube. If I was taking the cubed root of all of that, it would just be 6x to the 4th, one of those 3 identical factors. And again, I can do the same with prime factorization. Can 2 to the power of 6 be broken into 3 groups? Yes, because 6 is a multiple of 3. The exponent is a multiple of 3. The exponent is a multiple of 3. Yes, I can make 3 identical groups. Each group would have 2 2s, it would have 1 3, and it would have 3 7s. And I could do that 3 times, write it out identical, or I could just put a power of 3 up there and only write it out once, right? There's 3 of those factors. Same thing here. I would say no, it is not, because I cannot make 3 equal groups with 2 3s. Okay, so this would be a no, not a perfect cube. So, perfect cubes, you make 3 equal groups. The cubed root is one of those groups. So just a reminder from our powers unit, the negatives with our powers are extremely important when they fall inside the brackets or outside the brackets, especially with an even exponent. With an odd exponent, it wasn't as particular because 3 negatives makes a negative, and 3 positives made negative is negative as well. Okay, so when we get into square roots, we have to be careful as well. The square root of 81, well, it's 9 because 9 times 9 is 81. Well, what's the square root of negative 81? What times what gives me negative? Well, if I made it negative 9 and negative 9, it'd be positive. If I made them both positive, it'd be positive. I can't make one positive and one negative because that's not the definition of a square root. So the square root of a negative is not a real number. Okay, we cannot take the square root of a negative. If you tried it on your calculator would say error. What's the square root of 49 times 9? Well, since 49 is a perfect square and 9 is a perfect square, I can just take the square root of 49 and take the square root of 9 and say the square root is 21, right? Just like with variables. The square root of 16x squared, the square root of 16 is 4, the square root of x squared is one of them, x. So when you do take the square root is an operation. It's like a verb in English. It's telling you to do something to what's underneath. When you do that operation, when you apply it, when you take the square root, don't write the square root sign anymore because you've already applied the operation. So the cubed root tells you to break it into 3 equal factors and take one of those 3 factors. I've done that, so the cubed root sign does not get written anymore. Here, can you take the cubed root of negative? Well, let's see. This, since it's cubed root, I want 3 equal factors. And I know 6 times 6 times 6 is 216. If I made them all negative, would that product be negative? Oh yeah, 3 negatives make a negative. So you can take the cubed root of a negative. All right? You just cannot take the square root. Get it? Like even, right? Square root, there's really a hidden 2 index that we don't write. even indexes, you cannot take roots of negatives. Odd indexes, you can take roots of negative. If I want the cubed root of this product, again, I can just take the cubed root of 27 multiplied by the cubed root of 8 multiplied by the cubed root of 64, and then I can multiply those answers together. Again, once I've taken the cubed root, I don't write the cubed root sign anymore, so I get 6 times 4 is 24. That's the cubed root of that product. And again, with variables, we can take square roots of variables. Square root means break it into 2 equal groups. So it would be x to the 3. I can take the square root of 9, and I can take the square root of x to the 24. Right? I can take the cubed root of powers by breaking it into 3 equal groups. Right? I can take the cubed roots of numbers multiplied by powers. The cubed root of 8 is 2. And the cubed root of x to the 36, well, x to the 36 would be x to the 12 times x to the 12 times x to the 12, right? Exponents you can just divide by 3. You could not just divide the 8 by 3 because it's not an exponent. You have to find 3 things that multiply to give the 8. But since it's an exponent, you can say it's 12. So be careful between exponents and actual numbers, what the number actually is. 8 is not an exponent. And again, you can problem solve. For example, if you know the area of a square, you can find the side length of that square by taking the square root. So now we know this baseball field diamond is a square with side length 90. So if you had to run all the way around the bases, you'd be running 90 times 4 feet. If we wanted to know how far it is between one base to the other, it's 90. If I wanted to know how far it is from home base, the second base, I can use my Pythagorean theorem. Now that I know that each side is 90, I can say 90 squared plus 90 squared equals, and we'll call that x, the hypotenuse squared, right? And then we could go ahead and calculate that and go 90 squared plus 90 squared is 16,200, and then we take the square root to undo squaring, so we take the square root of that. And we would get approximately, since it's not a perfect square, we have to estimate 127.3 feet approximately is the distance. And if I had a cube and I gave you the volume, given the volume of a cube, we can always find the side length of the cube. Since we know the side length is x, and since it's a cube, they're all the same. We know that x cubed equals 343. So if we take the cubed root of 343, we get 7. So now I know the side length is 7. So if the side length is 7 and we want to find the area of one face, the area of one face is length times width, or 7 times 7 is the area of one face, which is 49 square centimeters. All right? So that is square and cubed roots.